Hi and welcome to my last winter project, and this is this sensor here, the MPU-9250, the I2C sensor, which has an accelerometer, a compass sensor and a gyro. We want to connect this one to the Raspberry and use it in Node.js. Node.js has no working node anymore, so we will create our own one and we will use Python for that. Python in Node.js to read out the sensor. So that's interesting because you learn a lot about mathematics, about electronics when you deal with the sensor. Several aspects you have to consider. So let's go! Yeah, we also need to do some theory, and today we will look at the accelerometer, so one of our three sensors. It's obviously measuring acceleration in 3 dimensions, so let's call this y, z and x. And when we have a static situation, there is one acceleration, and that's gravity. And gravity is 9.81 meters per square second, but our sensor is measuring in g, and this is obviously 1g. So this 1g will always be divided between our 3 different vectors. We can rotate the system around the z-axis, around the x-axis, and this will change the vector split. If we rotate it around the y-axis, nothing would happen because the gravity is still the same on all 3 axes. We also have a gyro and a compass sensor, but this is something which we will not cover today to focus on acceleration. So let's assume we have our normal coordinate system here, and we have our sensor somewhere here in this room. If we put it there and we put it in the position that the y-axis is in the same direction like the gravity, we will get a reading of -1g on the y-axis and 0g on the x-axis. Let's forget the z-axis for a moment and just focus on these 2 axes. So yeah, that's exactly what we would have expected, and if it's well calibrated and if there's no movement, we get this reading. And now let's rotate our system. So we rotate our system about the z-axis, even if this is not drawn here. And let's take an angle of about 45 degrees. What would happen now? The gravity, of course, doesn't change. So we have it in the same direction. And this g will now split. The y-axis, so the element which is measuring gravity in the y direction, will still get a reading, but now also the z-axis get a reading, and both would get a reading of, let's say, 0.5 minus for y and 0.5 for the x-axis, and this can be calculated to the 45 degrees now if we do some trigonometry. And that's what is provided by our sensor. Our sensor provides the y vector information in g, the x vector information in g, and the z vector information in g. So for this simple example, y and x would be enough for us to calculate this angle here. This is the rotation angle, let's call it theta, about what the system the system has tilted about this angle. We get it in g, but we need to calculate the angle. For that we need some trigonometry. So let's draw our system again, and I will just change a little thing. I will put the y-axis and the x-axis so that you can see that there is always, of course, a 90-degree perpendicular system, so a 90-degree angle between the y and the x-axis, and we want to calculate this angle theta. So you could put it to the x-axis or to the y-axis, then it's just always a difference to the 90 degrees. So we have a triangle with beta and alpha, and it's a perpendicular triangle with 90 degrees. So of course beta plus alpha must be 90 degrees to get the 180 degrees full. This also means, because we have 90 degrees here between the y and the x-axis, that theta plus beta must be 90 degrees. So that's now easy to calculate. You see it that beta must be equal to theta. So we can now calculate beta to get theta, and this is in a 90-degree triangle quite easy. Because in a rectangular triangle we just need some trigonometry to calculate the angles. So let's take A, B and C. So C is our hypotenuse. We have a B. B is for the angle theta, our adjacent side, and then we have our cathesis with A. And we can calculate this with the tangents of beta, and that's then the A divided by B. And then we can calculate the angle beta, the one we are looking for, with the arc tangent of A divided by B. So that's a simple calculation. They are much more complicated, but we will start with this one for ideal conditions. Okay, enough theory. Let's make our little first exercise. Again, what you need to have installed is Node-RED, of course. You need to have installed two additional libraries. One is the Python function, not the shell, the Node-RED control Python function. This gives us in a second this extra node to code Python directly within Node-RED. And you should already install the dashboard, the standard dashboard for Node-RED, because we want to see some values on our dashboard later. But we start without the dashboard. We start with our inject node, of course a debug node. And now our new node, which you find in functions, that's a Python function. This is only working what we are going to do now if you have already your I2C MPU-9250 connected on your GPIO header on the Raspberry, and you need to have Python installed on your Raspberry, as well as the I2C development tools. I will give you the code to install this just to make sure that everything is prepared properly. And remember also, you need to have your interface enabled in Raspberry config. We don't do this together now, as I think that's something we did already in other tutorials, and you might know this. That's not our topic for today. Our topic is to write a Python function and to get our MPU addressed. And let's do the first exercise together. So Python within Node-RED, and we can import Python libraries, and we need definitely SMBus, which is important to access I2C interfaces. We will need later on the math library for calculations. And then we need some registers. So first of all, what is the address of your MPU? In my case, it is hex 68. And then it's also important to know on which, maybe we do this before, on which bus you're working. The Raspberry 4 is using bus number 1. So we define this already in the way SMBus is using this later. I will show you this in both ways. So with our defined bus constant, but you can also see how this is working usually. So that's valid for all modern Raspberries. Raspberry 3 and 4, it's always 1. So, and then we should take also the registers we want to read out, but maybe we do this in our first example without definition, we do this directly. So to read out a register, we need first to have a read command, and there is a read command existing in the SMBus. library, and this is called SMBus. And now you have to define which bus. We did this already above, but to explain this, I will use this one first. Okay, now we have said, okay, on bus number 1, we want to access for a read of a byte, so of 8 bits. And now we need to define on which address, so that's the MPU, so the 68 in hex, and which register we want to read. And for that, you need the register map. I have this open here. That's the register map for the MPU-9250. And there are a lot of registers in, offsets there for the gyro, offsets for the accelerometer, for calibration. There are configurations in, and of course there are registers to just simply read the current value, the output. And to keep it simple, we start with that, and we just read out the X value. Unfortunately, this is an byte, 1 byte, so 8 bits here, but all values have 16-bit. So that means you have a high byte and a low byte. And you need to read out both. I will show you how this is working, and that's the first example we're doing. But first, take a look at the address, decimal 59 hex 3B. That's the high byte. And the low byte is 3C or 60. So always +1 is the low byte. And that's true for all other cases here as well. So when you have the temperature high byte on 41 hex, +1, it's 42. So let's take this 3B here first. And we want to read 3B. And maybe we also read 3. And let's put this to a name. So that's our X high. And maybe we put also acceleration in front so that we know, oh, that's the X-axis for acceleration and the high byte. And let's also read the low byte. We can maybe take this one now and use our nice definition above. So that makes it quicker. We can do the same here as well, of course. This was just to explain what we did here to get this easier. And here we take 3C. When this would be a variable defined here, we could just take the variable +1. So something like this would be the same result. We do this later. Let's start it simple. All right, and now we have both values read out. Maybe we test this, and maybe we return as in first example the high byte. Let's deploy and let's start. And you see we get an undefined, but the system is running, so we didn't get any error message. That's already good. That means that our system is working. And now you could ask, but why don't I see anything? And the reason is, let's take this payload thing. We just see payload currently. Let's take the complete object, deploy again, start. And you will notice there is a number, and this number is not on the payload, and that's our high byte. So in our high byte, we see currently, you can switch between hex and decimal F2. We will see later on how this is also working on the payload level, but then we need to define an object within our Python node, which has already the name payload, and then we return the payload as an object. But we do this later. The first thing we want to do now is to get one word. So currently we have the high and the low byte. What we want is something like this. So we want the acceleration of X. And yeah, the easiest thing you could think of is let's just add those two. And that's not that wrong. And then later on we want to send this one back. That's not that wrong, honestly, because what we need to do is to add both. But first, we need to get the high byte also on a level of a high byte. So we will shift the high byte, and I will show you a little graph how this looks like, just 8 bits to the left. And now the high byte is nothing else than a real 16-bit word with a lower byte of 0, of course. So, and when this is done, then you can add the low byte, and we will get a word, and we will get our complete value. So let's take a look again. Now you already see that's the nice thing on hex numbers. On hex, you always have the high byte on the left, this was F2, and the low byte on the right, that is 20. Unfortunately, this doesn't work in decimal. So when you take a look in decimal, you can see that left and right, this is not working because this is not on a base of 2 and 8 and 16 and so on. It's decimal, it's base 10. But because hexadecimal is based on 16, this works very well. So we can see that this was now shift to the high byte, and the low byte was to 0, which we didn't see because we didn't handed this back up to now. So that's how we read registers and how we create one word out of it. And we can now do the same, of course, for y and this z axis, and then we would already have all accelerometer values read out. Maybe as a last little exercise, so when we do this, I will just simply do this. Wait a second. So what I did now is I added just y and z. Of course, we need to change the addresses here. So it's 3b, 3c, then the y, 3d, 3e, 3f, and then there's, of course, after f 40. And so we have all the different bytes read. We create words for each. Oh, you see my mistake here. I didn't change these letters. And of course, we don't want to just return the x value, but let's take first a look if it's working. No errors. So it's still working. You see that the low byte has changed a little bit. That's already some noise because I didn't move the sensor. But now we want to return something which is a little bit better than just one value. And now we can already also solve the problem with our message and payload. So I will define now a new object. I will call, maybe we should do some commenting here, object for output. That is our calculation of words, and this is read out of 3 axes of accelerometer. So our message definition, and now we're going into Python basics. So how do you define an object? There are several ways. I prefer this one. For this task at least, I would say I want to define an object called message, and inside this object I need the first subcomponent, so the first attribute, and I call this payload. Oh, sorry, just payload, because we have message already. And within this payload, I will do another, but a subcategory. So this is again an object with following parts. Now I can define a name. Let's call the first one AcceleroX. And now you can say, okay, which is the value for that? And that's of course our X. Next one is Acceleroy. Now you need to keep in mind that if this is the name, you need the, how do you call this in English? High comma ters is maybe the wrong value, wrong name, wrong word. I will look this up later. And then it's Y. And last one is our set and set. Oh, and the right symbol here. done, deploy. Let's start it. Oh, and we need, of course, to return this one. I still return the x value. We want to return the message object. Let's say OK. And now you see already that we get an object back. It has no topic. It has a payload now, and the payload is an object, not just a value, because we defined an object. And within the payload, we find our accelerometer X, Y, and Z. And by the way, also a payload can be defined easily. Let's take for the same, for the message, another name, and this is topic. And we just define now a value for that, and we call these MPU-9250. Done, deploy, and we get a topic. We get an object, everything we need. Now we can switch back from our message, from our debug node to the pure message. Just the payload is enough for us. We deploy it again. And when we now take a look, our payload is defined with the values of our accelerometer. Of course, there's also still the topic, not as an object part, but here is at least the name, because that's always in the header. So I think this is enough for our first part, some theory and the first tries and trials to read out with Python our data of our accelerometer. And we created already an object which is in a node-RED way to deal with the values later on. But believe me, there's a lot left to do. This is just how to read out the values. We need calibration. We need to see how we write into the registers, especially the offset registers is tricky. So subscribe, because otherwise you will not get notified if there's the next part for this tutorial. And yeah, see you on the next one.